Hi, my name is Natalie Williams, and today I'll be presenting my lab on Lab 3, which is the black hole lab. So the first part is finding the mass of the black hole. So the goal of this lab is to generate a unique star trajectory that is based off of my email address, and to analyze the star's motion to find the net force of the motion, and then using that net force to calculate the mass of the black hole using fundamental physics principles, which we will then use to calculate a ship's escape speed. And the mass of the black hole, just for a quick preview of the result, is quite large in magnitude. It's 2 to 10 times 10 to the 34th kilograms, so quite large. So the key concepts we use are Newton's second law of motion and momentum principle, the product rule for differentiation, Newton's universal law of gravitation. But first we want to establish our system, which is the system is a black star and the surroundings are the black hole in this case. And then later we'll see that the system is the ship and the surroundings of the black hole and the planet that it comes off of. And here are the different formulas we will use. And then you can pause this again to look at the parallel and perpendicular components of the momentum, which is used in circular motion. So firstly, we want to calculate the different parts of our system. So we have the gravitational constant, the mass of the star, and the seconds in a day, which is the time between our data points, and it's just how long it takes Earth to make one rotation. These are the initial conditions of the system, where the system is the star and the surroundings enacting the force on the object is our black hole. So initial and final velocity are given in the code, but we need to calculate momentum. So we use Newton's second law and fundamental principles to find this, which I have labeled here. And here we are calculating the net force on the object using Newton's second law momentum principle. And then lastly, we do the perpendicular and parallel components of the force, since this is circular motion. Here we apply Newton's second law to the circular motion of the system, and this is due to fundamental principles, which concludes that the net force is equal to the sum of the perpendicular and parallel forces in this case, since this is circular motion. Now we apply Newton's law of gravitation. However, the arrow scale must be really small in magnitude for our visualization, since we use a large scale in reference to the star black hole and our gravitational pull, as these numbers are quite large. So therefore, we use our perpendicular, parallel, and gravitational forces, so 3 different forces, to visualize the motion. And you can pause this video at any time to look at the code. So here we have our diagram. It's the free body diagram. Parallel forces in pink, but its magnitude is so small comparatively to our orange and cyan that it just doesn't even show in the visualization. So orange is gravitational and cyan is perpendicular force due to circular motion. So here we have the results of this. We use Newton's law of universal gravitation, but instead of solving for the force, we rearranged to solve for the mass of the black hole, which you can see here. And the mass of the black hole was what I mentioned previously. You can pause to look at that. So what does this mean? How are the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? The rate of change and its momentum describe effect on our system, while the net force and its components are the cause totaling each effect, which means that they're equal according to Newton's laws. So part 2 is we don't want to crash our ship into the black hole, or we want to get close to the black hole, but we don't want to crash with the orbit of the planet around the black hole. So the initial velocity we calculate, and I'll go through the next steps for that, which is we use the mass of our black hole, which we previously calculated, which is now our surroundings. And here we have the system parameters of the ship and the planet and the surroundings. Here we calculate the velocity using Newton's law of gravitation. However, we have to alter the direction and magnitude so the ship gets close to the black hole, but doesn't crash into it. And therefore, I'm kind of messed with it and multiplied it by scalars. So calculating the net force on the planet via the gravitational forces interacting with each system / surroundings will give us these forces and the relative distances. And here we calculate the net force on our spaceship, treating it like a system, or it is actually the system, let me say, not like, as the system. And then lastly, we use Newton's second law and position update to calculate the planet's velocity and its subsequent ship velocity, where we rearrange to solve for initial velocity. So for my diagram, it found that it doesn't orbit the black hole because the mass of the planet is so great, and it cannot go to very close to the black hole and will not do a circular motion. Otherwise, it will crash. So I found that the x-axis initial velocity is, and this is with direction, negative 4.88 times 10 to the 7th meters per second, while the y-axis is 1.98 times 10 to the 6th meters per second. And these are the minimum velocities needed to escape. Again, I had a hard time calculating this because of the mass that my email generated. So this is why it does not orbit. So what if instead of wanting to take a quick look at the black hole and leave, we decided we wanted to enter into an orbit around the black hole, and so on. So the escape velocity does not take into account the direction or motion of the escaping system, thus the initial velocity must be the same as the one calculated. However, the direction and its velocity after leaving the planet would have to change in order to orbit the black hole. Right now it flies past it, but it doesn't really orbit it. And that is all. All right, thank you.